Hi, and welcome to my channel, JaberTime. Today I'm going to go over tangent planes and linear approximations. The graph here says a lot, but not the whole details. But at least it gives you an idea that we have 3-dimension. We have the surface S. We have the tangent plane in red. We have the point that the tangent plane touches the surface S. And we have more details, as you could see. This equation right here is the equation of the tangent plane. And for the linear approximations, we're going to talk about dz, delta z, and the difference between them. Let's get into it. Now, here's from a previous video, which I'm going to put down below. We talked about partial derivatives, and we talked about C1 and C2. So let me not go over it now and save you some time. If you want to see where C1 and C2 came from, just watch the previous video, which the link will be down below. This tangent plane in red sits on top of the surface, touches the surface at the point P, and contains the tangent lines T1 and T2. T1 is the one that goes with X when Y is fixed, and T2 is the one that goes with Y when we fix X. One more time, here's the graph, just like quick reference as we go. Tangent planes. Any plane passing through the point P right here has an equation of the form A times X minus X sub 0 plus B times Y minus Y sub 0 plus C times Z minus Z sub 0 equals 0. Rearranging, we're going to have to look at it from a different point of view and a cleaner look. Moving this to the right side, I have a minus. Dividing by C every single term, I have A over C here, B over C, I have a negative here. Switching natives or switching sides, move this to the left and move everything here to the right, and renaming A over B once it becomes negative to little 1 over C with the negative sign to little a, and B over C will be on the right side negative. We're going to call that little b. So now on the left I have just Z minus Z sub 0. Moving Z sub 0 to the right side will give me the following. I'll show you in a minute. If this equation represents the tangent plane at point given to me, then the intersection with the plane y equals y sub 0, y equals y sub 0 will be right here, will be the tangent line. In the previous video, we did the same thing, but when we set y equals y sub 0, we had the surface only, we did not have the tangent plane. The intersection was C sub 1. The intersection with the tangent plane will be the tangent line T sub 1. That is what is happening right here. If we set y equals y sub 0 in the equation itself, look what happens. Instead of y, we're going to write y sub 0. That means this whole thing will cancel. So you end up with Z minus Z sub 0 equals A times X minus X sub 0. Of course, you have to mention that because that's what you get when you put this as a condition. And it's kind of interesting to look at it from the point of view as point slope form in algebra. Recognize these as the equations in point slope form of the line with a slope, not m here, it's written as a. So this right here is a line. Point slope form for this line is Z minus Z sub 0 equals A times X minus X sub 0. So this would be the slope. But in the previous video, we found the slope for T1 by the first derivative, setting y equals y sub 0 and finding the first derivative with respect to x. So to make a connection, we're going to call the slope as the first derivative with respect to x, because we are going with x, and that would be the slope of t sub 1. Same way, if you want to fix x to be x sub 0 right there, and you're going to walk with the y, you're going to end up with t sub 2. Setting x equals x sub 0, this term will cancel, and you're going to end up with z minus z sub 0 equals b times y minus y sub 0. Of course, b, same concept, will relate to the first derivative with respect to y at that point x sub 0, y sub 0. So this is the equation for t sub 2, the tangent line, and this is the equation for t sub 1, the other tangent line. And the surface will be the surface that contains or made out of or built of t1 and t2. Imagine if you have two tangent lines or two lines in space, you could put a paper on top of those two lines if they intersect, and it will hold it. That is my tangent plane. Imagine if there is not anything else graphed, or the surface is not there and the x-axis and y-axis are not there. All what you see is a tangent plane with two lines on it. So that's t1, t2, and the tangent plane. Let's make this simple and quick. This is, as you can see, it's all kind of like a lecture where and how things are connected. Suppose f has continuous partial derivatives. An equation of the tangent plane to the surface z equals f of xy at this particular point will be the following. These slides are from Calculus 1, Linear Approximation, and I'm not going to go over it in detail. I will put the link if you need more detail in the description below so you could watch it on your own. But quickly, just to give you a quick idea what's in it, if you have the curve y equals f of x, you have a tangent line at a, f of a. Notice at a, both have the same value, either the blue line or the curve in black. But if this is 5 and you want to go to somewhere here like 5.01, we want to graph it next to it right there. It's kind of hard to see what's happening. So if 5.01 is right here, now you could reach out to the graph itself, that's called actual value. You could reach out to the line itself, that's called approximation. And doing more math from Calculus 1, you could see the right triangle with the derivatives, delta x, dx and dy. Or you could see it from delta y, as you could see here. That's the original y value, and this is a new y value, and that will be called delta y. Anyway, if you need more details, just go and watch that video and you'll have a clear idea about what's the difference between delta y and dy and so on. Those are more graphs. Notice the tangent line looks like ours in 3D. Same concept. This would be actual. This would be approximate. This would be the approximate, which has two pieces, and that's why it's like the start and some more. They used Lx in Calculus 1, and we're using L also, but L of x and y. This is from the Calculus 1, just to give you an idea. Now let's stay with Calculus 3, vector calculus. Now this is our point AB, 0. When you want to have a point near AB, that will be this point. I know it's graphed far away, but we just want to see the concept. A plus some change in x, and B plus some change in y. Of course, Z is going to stay 0, because we are staying on the xy plane. This much up to this point will be the actual f of AB, which is identical to this much right here. Now, if you want to go from this point, which is near this point, up to the curve or the surface itself, that will be actual. If you want to approximate, you reach up to the tangent plane, and that would be approximate. And there's a difference between them, as the graph shows. And that's the approximation and the difference between delta z and dz. This is the tangent plane in gray equation. And I think it's good enough to talk about those pieces. There is more, but let's just move on. This would be a good reference to understand the deep concepts of this section. Now, find the tangent plane to the elliptic paraboloid z equals 2x to the second plus y to the second, which is like a graph of a parabola that opens up in 3D at 1, 1, 3. First, let's find the slopes. This is the slope of t1. This is the slope of t2. Find the derivative of f as a function of x and y with respect to x. This will be 4x. This will be 0, as you could see. Plug in 1 for x and you get 4. The first derivative with respect to y, this will be 2y. This will go to 0. You have 2y, plug in 1 for y, and you get 2. Now I have the slopes. I'm using red, blue, and green for the point to show you where everything is coming from. And I have this as an equation of the tangent plane. Now it's with the numbers. That's my z3. That's my x z sub 0, which is 3. This is x sub 0, and this is y sub 0. The slope right here, 4, and the slope right here, 2. That's slope of t1 and the slope of t2. A cleaner look for this using simple algebra will be z equals 4x plus 2y minus 3. This is a plane. Linear in x and y and z. That is a plane. That's the tangent plane. Linear approximation. The tangent plane to what we just talked about at 1, 1, 3 was found in the previous slide as follows. The linear approximation. So now they want to distinguish between f and z and l, and there's different names, but you have to be careful. It doesn't matter if it's called z or f or l, you just have to be careful. This is the surface. It's a second degree. This is linear. This is the tangent. To make it more clear, we're going to call the tangent L, even though in calculus 1 was L for linear, or for the line, for the tangent line. But here, to keep it consistent, they're using L for the word linear approximation from being curved or a second degree or third degree. So this would be the approximation instead of reaching up to the curve. You remember the graph, and I mentioned that you have a tangent plane which is gray. This would be a good approximation, but when you're close, when you're near 1, 1. It was built and made when you are at 1, 1. This is a tangent plane at 1, 1. So if you want to use this tangent plane to approximate things at, let's say, 5, 7, that's going to be away far from 1, 1. So it's not going to be a good approximation. Just keep that in mind. So this was made for that particular tangent line, close or touches the surface at 1, 1. The function L, this function being called L, is called the linearization of f at that particular point, 1, 1. The approximation between the original f x y and the new linear expression, that would be called approximation, is called the linear approximation to the tangent plane approximation of f at 1, 1. So instead of using the original 2x squared plus y squared, we could use this as an approximation near 1, 1. So here's a point, 1.1 0.95. That is near 1, 1. So if you use the approximation, we use 4 times 2 times minus 3, as you could see. If you use actual, you take it from here. 2 times to the second, as you could see. And compare both. That's 3.3, that's 3.3225. And that's a good approximation. But if you want to go to 2, 3, 2, 3 is way far from 1, 1. Look, the actual, that's F right here, is 17, and the approximation L from the tangent is 11. That's not a good approximation. Hopefully that's clear now. Theorem. If the partial derivatives fx and fy exist near AB and are continuous at AB, then f is differentiable at AB. Show that f of x and y equals x times e to the xy is differentiable at 1, 0, and find its linearization there. Then use it to approximate f of 1.1, negative 0.1. Let's find the slopes. F of xy is written again. The first derivative with respect to x, you use the product rule and the chain rule. Plug in 1 and 0, that's my point. So that's the slope of t1. Let's do the same, but for t2. Derivative with respect to y, same thing, use the product rule and the chain rule. Plug in 1 and 0, I got 1. Same slope, that's what we have. Both f of x and or f with respect to x derivative and f first derivative with respect to y are continuous. So f is differentiable by the previous theorem stated. The linearization is what we called it. This is the new function. All right. That's kind of like z sub 0, if you remember. I'm using the same colors as you could see. So here I have f of 1 of 0, just plug in 1 and 0. In the original function, you'll get like 1 times e to the power 1 times 0. That's going to be 1, that's going to be 1, it's going to end up 1. This one right here is this one right here. And this one right here came from the second slope. We have x minus x sub 0. We have y minus y sub 0, because y sub 0 is 0. Simplify, and I get x plus y. This whole thing has a tangent that looks like this. Where at 1, 0. This is my original function. This is my tangent plane at 1, 0. This would be approximately equal to this near 1, 0. At 1.1, negative 0.1, we have 1.1 minus 0.1. I'm using this as an approximation to my original function that was called f. So we use the tangent plane to approximate. It came up to be 1. Let's find the actual. The actual, you have to plug it in the original function. As you could see, that's the original function. It's 0.98542, which is close to 1. So that one was a good approximation to the actual value. Now, here's the graph that shows enough details about the tangent plane, which is in gray, and this is its equation. If I move z sub 0 to the right side, that's going to be called f of AB. That's f of AB, this much right here. Now, these two are in red because I'm telling you what's the name of it. to stay focused. That's dz. So what's f of x, y, which is z? It's actually c sub 0 plus dz this would be the approximation. This right here is f of x, y, will be approximated to this value all the way up to the tangent plane, which is two pieces. This is f of ab and this is dz. So what's dz in a different way? dz is dz dx times dx, that's a difference in x, dz dy times dy. Delta z will be this much right here, which is f2 minus f1, instead of calling it y2 minus y1 like calculus 1. So it's going to be f of a plus delta x and b plus delta y minus f of ab. Z equals f of x, y is given to me as x to the second plus 3xy minus y to the second. X is changing from 2 to 2.05. That means delta x is 0.05. Y is changing from 3 to 2.96. So delta y is negative 0.04. Compare the values of delta z and dz. Here's delta z. Just plug in the points. Look at this one here to start. A and b, that's 2 and 3. That's a and b. That's a plus delta x, and that's b plus delta y. So we plug in 2.05, 2.96. That's my new location, minus the original one, which is 2 and 3 for a and b. Just do the math and plug in these numbers in our equation. We have 0.6449. Let's go the other way, which is dz. dz will be dz dx, that's f of x sub 0, y sub 0, which is f of ab with respect to x as a slope derivative. Then plug in the numbers for a and b. This is the derivative of this with respect to x. Let's double check. 2x, 3y, and this will cancel. 2x plus 3y. Plug in a and b. That's my a, that's my b, or that's my x sub 0, y sub 0. Here we're going to find the derivative with respect to y. That's a slope. With respect to y, that's going to be 0. That's going to be 3x, and that's going to be minus 2y, as you can see. Plug in a and b, 2 and 3. dy is the same as delta y. That's delta y. Delta x is same as dx. So I have 0.65, and here I have 0.6449. Why they're close? Because the point that we are using is close to the original point. We're going from 2 to 2.05, from 3 to 2.96. That's a little bit kind of like the difference. Okay, that should do it for now, and I'll see you in the next one. Thank you for watching. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.